Let's take a look at our lesson for today. We're going to be looking at vector equations of lines in space. That is our job for today. So if you'll take a look at this, hopefully you remember this from when we were in our, actually the last unit, the parametric and vector unit. Recall how this was the vector equation of a line, and we would pull this apart to create a parametric. Remember how we would say x equals, and then we pull that first spot plus t times the second spot. Remember that? And then we would write the y. So you've seen this equation before, or we've worked with it when we were working with parametrics. So that's the equation that we're going to be working with today. Actually, more specifically, we are going to be creating this. Okay, that's the equation that we'll be working with. So let's talk about what each of the parts means. What is, r? So what's r naught, etc. So r, this position, is basically the vector in x, y, z. It's like the equation. So it's the position vector to some variable point on the line. That's what r is. R naught, the second location, is a stationary point on the line. Remember when we created this, we chose this point on the line. Remember we were parametrizing a line. We would choose a point on the line, and then we would write a vector. We're kind of going, basically we're creating that. This would be a point, or basically it's a specific point on the line. It's a position vector to a fixed point on the line. Then we have v, our vector. This is our vector that is the direction vector. We talked about direction vectors yesterday when we were looking at direction cosines. We actually talked about direction angles yesterday, but this is the direction vector of the line. This v is the direction vector. It basically, is parallel to the direction of the line. All right, and this t is the parameter. Now, it doesn't have to be t. It doesn't have to be the parameter t. It could be a different parameter. In fact, you probably wouldn't guess this, but I love reading like Precal textbooks and calculus textbooks. I love that, right? And so some textbooks, actually one that I was working with, use a d here instead of a t to basically describe distance. So you can have a parameter with distance, and you could use a d there. That would be fine. Or you could use t for time. This is the vector equation that we used in Calculus 3, which is the reason that I'm using it now. You don't have to use a t. You could use some other variable as a parameter, is all I'm saying. So that's our end goal, is to create this vector equation of a line. So let's kind of see what it is we're doing, kind of a visual look at what we're doing, a geometric look. If we take a look at this graph over here, notice that r naught, we said that was our specific, it was a vector to a particular point. Notice how r naught is going to p naught. That's a point, right? So r naught is our vector that travels to a point on the line, a specific point on the line. Then r travels into general, basically to x, y, z, to some general point on the line. So here's our r naught and here's our r. This kind of diagram hopefully looks a little bit familiar. Remember actually in last unit and this unit, when we would draw this to find, like, let's say we wanted the point 20% of the way from A to B or something like that, or 1/3 of the way from A to B. Remember how we would draw two vectors from the origin, and we would have like this kind of triangle looking thing? That's kind of the visual that we have here. It's nothing new. We've done this before, but we have in a new context. So we have our vector going to a particular point on the line. We have our vector going to, in general, x, y, z on the line. Then we have our direction vector. That's this right here, vector v. Vector v is in the direction of the line. It's basically parallel to the line. It's kind of sitting on the line. Okay, that's our direction vector. And our direction vector v, we are pairing with a t, with the parameter t. Okay, so this is the kind of the picture that we're drawing. And it took me a while to figure out how this works, and I just kind of want to explain to you how is it that we're having vectors coming out of the origin creating a line? I think that's a little bit confusing. So why don't we think about these vectors as they're pointers. The end of the vector basically is pointing at or touching the object that it's creating. So I have an infinite number of vectors coming out of the origin, kind of highlighting the path of the line. Does that make sense? That's what these vectors are doing. They're kind of coming out of the origin. I could draw, multiple vectors coming out of the origin, and they're basically highlighting the path of the line. That's kind of how that works. I know it's a little bit confusing, but that's really visually what's happening, is these vectors are mirroring, highlighting basically the path of the line. Mm-hmm. Yes. Yes, there are an infinite number of vectors that populate this line. That's exactly right. There's an infinite number that populate the line. Okay? So that's what we'll be working with today. Any other questions in general before we start the examples on the next page? Okay, let's go to the next page and let's write these vector equations for lines in space. So this was a point in Calculus 3 that a lot of students were a little confused. They really didn't have any experience with writing vectors. The equation was very confusing. So I'm hoping after spending several days on it that we'll be much more comfortable with like vectors in 3 dimensions and projections, cross products, those kinds of things. So let's jump into our first question. We are supposed to find a particular equation for the line that contains a fixed point, P0, which is at 5, 11, 13, and is parallel to the unit vector. So now let's kind of pull apart what we have. Just for fun, I'm going to just kind of do, and this isn't a perfect graph, I'm just sketching, right? So I'm going to sketch this line that we're trying to, so we're going to say this is line L. And we have a vector coming up off of here. This would be R0, and this would be to point 5, 11, 13. Okay, that's an 11. Okay. So 5, 11, 13. Okay, and then we have another vector coming out of the origin to a general spot on the line. This is vector R, which is the vector that we're writing, and that's in X, Y, and Z. Okay, so that's what we're looking for. And then what we have been given is our direction vector. This is called, this vector U is the direction vector. It's in the direction of the line. So this one is vector U. It's in green. And again, this is not a to scale graph by any means. I'm just kind of trying to show you the concept of what's going on. So that's what we're doing. Those are the pieces of the puzzle that we have. So in order to write our vector equation, let's write down our formula. So it's R0 equals, R equals R0 plus T times vector V. So that's our vector equation for the line. R0 is the vector that points to our specific point, our fixed point. So R0 is basically 5i plus 11j plus 13k. Okay, so that's the vector whose terminal point is the point on the line 5, 11, 13. That's what R0 is. It's the vector that points to 5, 11, 13. This vector, this unit vector in the direction of, this is our direction vector. This is our direction vector. And our direction vector is noted in our formula as V. Okay, so do we see all the parts of the puzzle that we have? We have our R0 and we have our direction vector. Now we're going to put all of those together to write our equation of the line in vector form. So I would do, I put R0 here, which was 5i plus 11j plus 13k plus t times, make myself a little bit of space here, my direction vector, which is 3/7 I plus 6/7 j plus 2/7 k. And that's how we looked at them previously. I mean, that's how we would have written them. We're going to do something different, though. We're going to bring it together. We're going to, when you see a vector written, see, doesn't it look like this, right? With the I components in front of the I, and the j components in front of the j, and the k components in front of the k. They're all combined together. That's what we're going to do to write the final form of this vector. We're going to gather together the I component, so it's going to be the 5 with the 3/7 IT. We're going to gather that together and put it in front of the I. Okay, so that's how we're going to finish this out. So our vector R is going to be, so we're going to pull the I components. So I have 5 plus 3/7 t, and that's our I component. Okay, plus, then I have 11 plus 6/7 t, and that's our j component. Plus, then I have 13 plus 2/7 t, and that's my k component. Now let's just talk about what we just did. This is the very first time that we have seen a variable in the z component or the y component or the x. Look, notice how we have a variable in there. We actually have a little expression. It's not just a number. That gives us flexibility into finding different kinds of points on the line. That's what that's what this does for us. Is we're introducing, we have now a variable inside of our x component and y component and z component. Okay? Questions so far? Are we okay with that? Okay, so this would be our vector. So now with that vector, we're going to be able to do some stuff. The part A says find the point on the line has a directed distance of -21 units from P naught. All right, so P naught is like our point of interest on the line. That's kind of our we could say original point, right? That's the point that we're measuring things from. So if I have P naught and I want to go 21 units negative, so like left down, right, from there, really that would have been kind of difficult previously, but now with this vector equation it's really not that bad. All I have to do, think of t as a distance. It's a distance, so really all I have to do is substitute or plug in a -21 for each t, and that's going to give me the exact vector that would point to that point. All right, so my R naught, or excuse me, my vector R, because we're working on -21 units away from P naught, would be 5 plus 3/7 times -21 I plus 11 plus 6/7 times -21 of j plus 13 plus 2/7 times -21 of k. So you would have a calculator to do the number crunching here. I don't expect you to do, I mean, I would like to use your time on more difficult things rather than, you know, doing all this addition and multiplication. So we would use our calculator to number crunch, and when we do, we get that we're at -4i minus 7j plus 7k. So what that gave us, it gave us the vector that's pointing at the point that we want. This point is 21, you know, negative from P0. So the actual point, so this is the position vector that's pointing to a specific stationary point, right? And my stationary point is -4, -7, 7. That is the point that is -21 units from P naught. Is that okay? So basically, we were able to find the vector that points to that point, right? That terminates at that point, and we wrote that point from the vector. And we found what we needed. Okay, so for part B, I actually think I had a typo on my notes. This should say XY plane, I think I wrote axis there. It should say xy plane. So we want to find the point where the line intersects the xy plane. Now I really wanted to do a lesson with planes. I just ran out of time. There's so much more fun stuff we could do with this unit, but I did not have time. So we're just going to have to kind of think about planes in general. So let's think about the xy plane. You learned about planes in geometry, right? A plane is a flat surface. Think of it like a piece of paper, right? So we have a plane. Think about, on this picture up here, think about what the xy plane means. The xy plane, every point that exists on this xy plane has one thing in common. What do all the points on the xy plane have in common? The z value is 0, right? The z value is 0, and they are coplanar, right? They're on the same plane, but the z value is 0. So if we want to figure out where our line that we just wrote intersects the xy plane, we're going to need to know when the z value is 0, right? That's going to give us the point where we intersect. So how are we going to find out when the z value is 0? Well, we would go up here to our z component and set it equal to 0, right? That's what we would do. So let's do that. Let's take our z component and let's set that equal to 0 and see what time, I think you can think of it as time now, what is our t value where z is 0. So I would move the 13 over, multiply by 7/2, and I get, oh, the beautiful number of negative 91 halves. That's going to be lovely to calculate with, right? Woo, negative 91/2. So how is that going to help me? Now that I know the t value of negative 91/2, how am I going to find that point? What would I do? What would I do? Absolutely, yeah, we're going to plug it into our equation up here. Our vector equation. We're going to put it everywhere there's a t. We're going to put negative 91/2, and that's going to give us the location, the actual point that this line crosses through the xy plane. So let's do that. So we'd have 5 plus 3/7 times negative 91/2 I plus 11 plus 6/7 times negative 91/2 j plus, then we'd have 13 plus 2/7 times negative 91/2 k. So we use our calculator, we do all that number crunching in our calculator, and we get our vector to be negative 14.5 I minus 28 j plus 0k. If we didn't get a plus 0k, we would have done something wrong, right? Because our z component needed to be 0 for this to happen. So this is the vector that points to, it terminates at the point that our line intersects the xy plane. So that point would be negative 14.5, comma, negative 28, comma 0. That would be the point. So let me check. So if I wanted you to find the point that our line crossed through the YZ plane, would you know what to do? Right, we'd be okay. We understand the concept, right? Or if I wanted you to find where it went through the XZ plane, you would know what to do, right? Set the Y equal to 0. Okay, so we're good with that concept. We know how to find when our line crosses through a particular, and that's as crazy as I'm going to get with you with planes, right? We're just going to look at the XZ plane, the YZ, and the XY plane. I mean, that's it, just those coordinate planes. Maybe some other time or some other day we can play with, you know, other planes. We'll see. All right, so our last problem. We have a line that contains 0.53 negative 1 and has direction cosines. So we're kind of blending yesterday's lesson with today's lesson. So what do you think this 0.53 negative 1 is going to do for us? How's that going to help us? Isn't that our R naught, right? Isn't that our vector to a particular point? So R naught is going to be 5i plus 3j minus k. Okay, so that gave us R naught. And direction cosines, let's think about that from yesterday. We remember direction cosines, right? What did we use direction cosines for yesterday? To find direction angles, right? Didn't we find direction angles with them? We also use them to write a unit vector in the direction of, remember that? Do we use them to write a unit vector in the direction of, wherever the line that we're looking at? So that's what we're going to use these for. We're going to use these to write vector v. This is the basis for our direction vector. Our direction vector, which is vector v. That's what these are going to do for us. And typically vector v is a unit vector. I'm just going to say, usually it's a unit vector. What's a unit vector? Do you remember what that is? It's a vector that has a magnitude of 1, right? And we know how to make unit vectors. That's when you normalize a vector. We learned that in the last unit, right? We know how to do that. Okay. So many times, like they gave us the unit vector here, we have the direction cosines, which will give us a unit vector when we write it. So our direction vector is typically a unit vector. So let's write our direction vector. So v would be 6/11 I minus 2/11 j plus 9/11 k. That's going to be our vector v. So to write our equation for the line, we just need to pull those things together. So we would have vector r is going to be our r naught, which is 5i plus 3j minus k, plus t times our direction vector. Our direction vector is 6/11 I minus 2/11 j plus 9/11 k. Okay, so our last job is simply just going to be to pull that together in the proper form. Right? We need the I components to all be together and the j components to all be together. So we're just going to combine those things into one little piece that has a variable in it, right? We're creating a vector which has a variable in the x, y, and z components. So we have the 5 plus 6/11 t, that's our I component, plus, then we have the 3 minus 2/11 t in the j component, and then we have negative 1 plus 9/11 t in the k component. And that is our vector for those lines. And if they wanted us to find different things with that vector, we could, right? We could find out where it crossed the xy plane, or we could find out different things for that. Are we okay with that? Yes? Okay. Great.